morning. You're all making telescope objective mirrors now. Most of you have done the coarse grinding. You're getting the curve, the depth that you want, so you get the focal length you want out of your telescope mirror. These mirrors are mostly going to be used in Newtonian reflectors. And pretty soon you'll be doing the fine grinding to get the surface smoother. Then you'll graduate to polishing, and then after polishing you're going to do the figuring of the mirror. The figuring is where you put the very careful shape into the mirror so that it can focus the incoming light coming from the heavens into a nice, sharp, crisp image that you expect out of your telescope. It would certainly, you'd like to have a nice, crisp image out of a telescope that you've made. I've got some material that I'm going to present to you, which is an introduction, if you will, to a little bit of optics, a little bit of the type of, I'm going to expose you to the type of tests that can be done to test the paraboloidal shape or other shapes of optical surfaces. And I'm going to highlight one or two of the tests in here because they're the tests that we're mostly going to be concerned with. But hopefully the explanations will kind of overlap and you'll get an overview of all of them. The material is in the form of a PowerPoint presentation, which I hope you'll bear with me, but the material has already been laid out, and I've used this for talks that I've given at Stellafane and at Okie-Tex, and I think it's pretty good. So bear with me, and hopefully you'll get a little introduction here as to how to do your telescope test. Okay, this list here gives you an idea of what I'm going to be talking about over the next few minutes. I'm going to be introducing to you the basic principles of the optical test and the null concept. And then I'm going to be discussing surface shapes and which surface shapes produce a null test or a null test return. I'm then going to define spherical aberration. Spherical aberration is important because that is what we are essentially correcting for when we're making our mirrors parabolic. I'm then going to show you testing a parabola by measuring spherical aberration zones. This is the familiar focal knife edge test. It's application of a test where you're measuring spherical aberration. And I'm going to introduce other tests that measure spherical aberration also to help determine whether you have a parabola. And then I'm going to be introducing other null type tests for telescope mirrors. Null tests are far superior tests, and we use a null test here. And hopefully, by outlining all of these principles, you'll understand what we're doing with our test and understand why the null test is so important. Let's consider an optical system. Our telescope is an optical system. It consists of an objective, which in our case is a mirror, and that mirror is supposed to take some light from some source, in our case, light from infinity or space. But an optical system doesn't have to be a telescope. It doesn't have to take light from infinity, but it takes light from someplace, and there's an output to that optical system. And if all the light from everywhere across that optical system comes to a focus at exactly the same point, that is generally the desired outcome of an optical system, for all of the light everywhere on the optical surface to come to a focus. That's what we would like. Now, if you have an optical system that does that, and you put your eye just a little bit behind where it comes to a focus, only just far enough so that all the light shines into your eye, what is it that you're going to see? Well, what you're going to see is an entirely uniformly lit up optical surface. Why? Because it appears to your eye that all of these rays of light are coming from uniformly everywhere all over the surface. Now, for most telescopes, the optical system is a round aperture, or a circular lens, and here's what it would look like if you had the output of your optical system, your lens, all of the rays of light coming to a focus, and you put your eye there. You see a uniformly lit up disc. Now, if I were to take that light cone, now I've magnified the area where it's coming to a focus. The mirror itself is way off to the left. And if I take a knife edge and introduce it into the beam, consider this a top view, considering that I'm introducing the knife edge from the right. If I start cutting that bundle of light and my eye is back here someplace, what am I going to see? Well, I'm progressively cutting that beam of light with the knife edge, so I ought to see a shadow coming across the aperture. And I do. I see a shadow as I introduce the razor or knife edge into that cone of light. As I continue to move it, then this shadow will act as a curtain and go across the surface. And if I withdraw it, then of course it will lighten up again. If, on the other hand, I take that same knife edge, still coming from the right, but instead of introducing it in front of where it's focused, I introduce behind where it comes to a focus, and I still have my eye back here someplace, the light bundle that I'm cutting originates now from the opposite side of the mirror from where the knife is introduced. And what do I see from that? I see the shadow apparently coming from the opposite side of the mirror, from the side that the knife edge is introduced. If I take then the knife edge and I introduce it into the output of the optical system right where all of the rays come to a focus, what I'm going to be doing is cutting that bundle of light. I'm going to be cutting every single bundle of ray at exactly the same time with that knife edge. The appearance will be that the surface will appear to gray and darken uniformly. And that's the appearance of a surface, all except the very edge there, graying and darkening uniformly. Now this is essentially part of what's meant by a null test. All of the light has come to a surface, come to a focus, and I get a uniform one result. If there are any imperfections in that surface, then they show up in bas relief as shadows on the surface. In this case, I have a fairly smooth mirror, but I have a depression in the center, and then I have a depressed zone out here. It kind of looks a little bit like a pie plate, or a pie actually, a little bit of a pie crust, in bold relief. And these shadows are really very sensitive. This is in the order of millionths of an inch, or certainly tenths of thousands, but yet they show up very easily. And that's why a test of this nature is so much fun to use. In addition, I could just have totally irregular errors, and those irregular errors will also show up as just blotches and roughness on the surface of the mirror, or the surface of the optical system. There's another thing I can do. Instead of having a single knife edge, suppose I have multiple knife edges very close together. We call that a raunchy screen. Now this is greatly magnified. It's showing a raunchy screen. But consider that what you've got is opaque bands and see-through bands, and opaque and see-through and opaque and see-through. So the light will go through those bands on the way to the mirror, and they'll come back through the bands on the return to your eye. What you end up seeing across your optical surface, if it's a focus and if you have a null condition, is uniform, straight, parallel lines. You started with straight parallel lines. In the test return, you get straight parallel lines. And this, by the way, this screen is not introduced right at focus. This screen is introduced either in front of the focus or in back of the focus. If it were right at focus, then one of those little raunchy bars will act as a single knife edge and create a graying and dulling of the entire surface if it's, everything is at focus. Now, if you take that raunchy screen and go further inside or further outside of focus, then the lines will start packing together. You'll get more lines across your optical surface. The test becomes a little bit less sensitive. And if the screen starts getting closer to the focus, then the lines spread out. In this case, you end up with one or two lines. And that's an interesting principle that we can use, because we have to realize that the closer the screen is to the focus for anywhere, the fewer lines you're going to have. The further it is from any focus, then the more lines you're going to have. What kind of a surface is apt to give us a null return? Well, a spherical surface will do that. A spherical, under certain conditions. A spherical surface, if you have a point source of light at the center of curvature, a sphere and a circle are so defined that all points along the surface are equidistant from one common point, called the center of the circle or center of the sphere. We will also call it the center of curvature. In optical terms, what that means to apply it optically is that any light ray that leaves that singular point will travel and hit the surface of the optic in exactly perpendicular and reflect exactly back to that same point. And if you move the light just a little bit to the left, then the reflection goes a little bit to the right, and if you put your eye there, you start out with a uniform surface. If you back your eye up a little bit and you start cutting the light beam, since all of the light comes to a complete unique focus right at that one point, that is a null condition. You'll get a uniform graying with a single knife, and you'll get straight, parallel, even lines if you're using a raunchy screen. There are other surfaces that can do the same thing, and we need to talk about them a little bit because they do have application in optics. What is an ellipse? Ellipse is, you're starting to stretch the circle now. Instead of having one foci, you end up with two. That you can't say that the surface is equidistant from any one place anymore, like you can with a circle, but what you can say is that the sum of the length of this line and this line is the same length, regardless of where these two lines go. The sum from here to here to here is the same everywhere in an ellipse. Optically, it has another important, interesting property, and you could work mathematically out the angles if you wanted to. But any light ray that originates from one focus will strike the surface at an angle that's such that it will reflect off that and come to focus at the second foci. So an ellipse has two foci, circle only has one. Any light source at one foci will come to a complete focus at the other foci. If you were to put a light source here and then put a raunchy screen here or a knife edge, you will get a null return. And that's important because there are tests that are based on this principle. One, for testing elliptical mirrors, and two, for approximate testing of a parabolic mirror if you have a very, very long ellipse. Because let's continue. We started with a circle. We started to stretch this circle. We got an ellipse. Let's stretch it one more time now. We start having a very long ellipse. And the principle is still true, that if you have the light at one foci, the light will then shine to the surface and then come back to the other foci. And I can keep stretching that ellipse, and I can get those foci farther and farther and farther apart. If I go far enough, I end up with another unique case where the foci are an infinite distance apart. And if they're an infinite distance apart, then the light coming from one foci is going to be a parallel bundle. And this surface now becomes a parabola. The ellipse just stretches towards a parabola. When you finally get the other foci an infinite distance away, you get a unique shape. It's called a parabola. Parabola means that light coming from a parallel source of light will focus to one common point. And that focus is going to be 1/2 the distance of what the, if you consider that to be a circle, at the center of curvature would be twice the distance of the focus of a parabola. So we can also get a null return if we do a test with a parabola and we have parallel incoming light. We can then put our razor blade or our raunchy screen at the focus. If we have a razor blade, we'll have a uniform cutoff. If we have a raunchy screen, we'll have straight parallel lines. And that principle was used in testing way back before we had any bench testing. Telescope makers would make their mirrors, they would take them out at night, they would aim them at a star, and they would perform this null test. You have to assume, of course, and hope that you get good enough weather conditions in order for you to get a good test. You could see that that became a very cumbersome, bothersome test indeed. So, let's take a look at some other principles here. Suppose we have parallel light coming in, and instead of hitting a parabolic surface, it hits a spherical surface. Well, a spherical surface is a little too curved at the edges and a little too flat in the center, and what's going to end up happening is that the light that strikes the edge of the mirror is going to focus closer to the mirror than light that reflects from the center of the mirror. That light is going to focus a further distance away. So now we don't have a good focus. A spherical surface will not focus light from an infinite source or a parallel bundle of light into a single unique focus. The light has to originate at the center of curvature in order to get a unique focus with a sphere. This aberration to the wavefront is called spherical aberration. This is the primary aberration that we are checking for or correcting when we parabolize the mirror and when we run our tests. Now, if we have a parabolic mirror, we can run a null test if we look for light that's an infinite distance away, but we know that that's complicated and very difficult. And it can be a little indefinite, and it can certainly make it hard for you to plan when you're going to do your test if you're going to use a star or some light that's a long ways away. So wouldn't it be nice if we could somehow test a parabolic mirror on a bench? There have been several ways devised to do that. One is to say, okay, for our telescope, since we have a fairly long focal length relative to the diameter of our mirror, maybe we can make the assumption that our parabola is close to some sphere, and that if we put the light at the closest center of curvature rather than at the focus, that the light will come off the parabola, and what is it going to look like? Well, we know that it takes a sphere to focus the light. We know that a parabola takes parallel light and focuses it. But a parabola with light originating at the closest center of curvature for the closest approximate sphere now is going to have reverse spherical aberration from parallel light focused by a sphere. What that means is that the light from the outside of the mirror is going to be focusing farther away than the light that hits the center of the mirror. Well, that's goodness in a way, isn't it? We maybe have a characteristic that we can use in conducting a test. Let's take a closer look at this region. When the mirror is a parabola and you have the light at the closest center of curvature, the returning beam is not focused due to spherical aberration, and when the beam is cut by the knife between where the center rays focus and where the edge rays focus, this line here, by the way, is called the line of lateral aberration. And we can cut the knife edge anywhere in here, and we're going to get an interesting result. Let's just consider that we've cut it about 3/4 of the way back. The light that focuses from the center of the mirror, we are now cutting that with a knife edge behind its focus. The shadow then is going to appear to come from the opposite side, from the side we have introduced the knife. Those rays that come and focus right under the knife, for that radial zone around the mirror, that's going to be gray and darken uniformly because I have nulled out that particular zone. The light rays that focusing from the outside part of the mirror are focusing farther from where I'm introducing the knife edge. The knife edge is then cutting the rays as they come to the focus so that the shadow outside of the null zone is going to have the shadow crossing the aperture the same direction as the knife edge. So what's that going to look like? Well, here's an example of what it looks like. This, by the way, is an f4 parabolic mirror. An f4, meaning that the focal length is 4 times the diameter. This is a fairly steep curve, and the parabola is a rather strong departure from a sphere. So the shadows are strong and evident, and I've used that in this example. Books do that too, but I can assure you that if you're using like an f7 or an f8, these shadows are going to be far less obvious, and I'll show you that in a minute. But the point is, I want to show you what this means. You can see now that I have a region here where the shadow is opposite. Remember, my knife is coming from the right, and I have this region here where the shadow is coming in the same direction as where the knife is being introduced. Right here at this zone, this one zone around the circle, it's gray. That's called my null zone, because at that circumferential zone on the mirror, I am cutting my knife exactly its focus. So that's a characteristic pattern of a parabolic mirror, and it's also a fairly characteristic pattern of some other shapes, by the way, that are similar and a little bit hard to detect, but we won't go into that here. Now what I want to show you is the same mirror, but an f7. And the reason I'm doing that is I'm showing you how much less distinct those shadows are. Your f7 mirror, the parabola is very close to the sphere, and therefore the departure from the sphere is little, and the shadows are not going to be very distinct. There's goodness and badness to that in conducting the test. You don't need to define quite as many radial zone points. You just need to do the center, the 70% zone, and the edge to know that you're going to get a good mirror if you're testing in this fashion. So now that we have defined spherical aberration and we have shown that the spherical aberration produces a predictable result in our test return, can we use that principle in order to define our parabola and know that we're going to get close? Well, the answer is, within some sensible reason, yeah, there is. There's several tests out there that attempt to, in some way, either in a qualitative way or quantitative way, measure against some predicted outcome of spherical aberration being introduced. And these are the 4 tests. One, of course, is the very common focal knife edge test. This is the most common test that you will read about. It's the easiest test for amateurs to do because it does not require any elaborate support equipment. All you need is a light source, a knife edge, and your test mirror, and enough fixturing to hold everything secure so that you can perform the test. We will also have the Raunchy screen, which I showed you, the Raunchy screen at the center of curvature. We're now not going to get straight parallel lines. We also have a wire test and a caustic test. Both those tests are a little bit far out. I'll touch upon them. I won't waste a whole lot of time with you, because I really want you to understand the focal knife edge test and the raunchy screen test the traditional way, and then I will tell you how we're going to do the test, which is a better way. Focal knife edge test. Again, we're going to consider we've got a parabolic mirror, it's on the bench, we've got the light source at the closest center of curvature, the light goes out to the mirror, comes back, we have spherical aberration introduced. This is the same picture I showed you before, but I got a couple of things added to it. One is I can very carefully predict what this longitudinal aberration line is going to be. The longitudinal aberration line is going to be equal to the radius squared divided by 2 times the radius of curvature. Now that radius, by the way, can be either the entire radius of the aperture of your mirror, if you want to know the whole length of this longitudinal aberration, or it will be the radius of your zone that you're trying to measure if you want to know where that zone will be nulled out as placed between the closest point and the farthest point on your line of longitudinal aberration. In fact, over here is where I say the knife edge at h squared over 2r, where h is the radius of your zone. So you can predict exactly with a parabola where this knife edge ought to be to null out the various circumferential zones on your mirror. And that's generally what you're doing when you're conducting the test, measuring zones. But now you realize, again, this is not a null test. This is a test that's giving you some interim result. That interim result is a table full of numbers. That table full of numbers has got to be subjected to some other kind of analysis in order for you to know whether your mirror is any good or not. But that's jumping ahead a little bit. Let's go back now to conducting the test. I got a mirror here. It's a parabolic mirror. It's the same f4 with exaggerated shadows. And I have a bar in here with some tick marks to show you the various zones so you can see. And I have placed the knife edge close to the front of that line of longitudinal aberration so that I have essentially nulled out the inner 30% of the mirror. And I mark that knife edge position when I'm conducting the test. Then I move the knife edge back some amount until I see that now I have, let's see, 10, 20, 30, 40. So I've got about the 50% zone grayed out, and I mark where my knife edge is in respect to where I started. And then I move the knife edge back until I get the 60% zone, mark where the knife edge is, and do the 70% zone and the 80% zone, and then go through the edge zone. Now, I showed you with a line and some tick marks just because I wanted you to see what was happening as you move the knife edge back. A common tool used to help identify those zones is this mask. It's called a Coder screen. It was developed by Andre Coder in Paris for his telescope mirror making. And the idea is that when you're at a certain zone, so you got the knife edge so that that window and that window, which are the same distance away from the center of the mirror, when they are the same gray, then you have put the knife edge where you're nulling out that zone. Then you move the knife edge back until these two are then uniformly gray, and you've identified that zone. So you construct this mask so that you can identify certain zones that you want to identify and gray and null and then measure. And what do you do with the information? What do you do with that table of results? I said you had to subject it to some other analysis in order to know whether you have a good mirror. One way of doing it is by plotting it up on a curve. This is a nice way to do it because these days with computers you can make an Excel spreadsheet and a graph, and it works very nicely. This graph here is a depiction. It shows this is the center of the mirror, and the diameter of the mirror, or the radius I should say, goes across on the horizontal axis, and your knife edge position is along the vertical axis. So we've got what's marked off here, the 20%, 40%, 60%, 80, and 100, and 120% zones. So what this means is that you can calculate from that formula where the knife edge ought to be to null out each zone. So you end up with the ideal placement, which is this blue line. And if when you take your measurements for each radial zone of the mirror, you come up with exactly a certain number of thousandths of knife edge position, and you can plot the points, and they're all nicely along that line, you have an ideal perfect mirror. Nobody ever gets there. Don't expect that. Also, what this curve depicts is some sensible boundaries. And these boundaries, there's a formula for defining that. This method came from gleanings for ATM, or amateur telescope makers, in Sky and Telescope magazine in February 1976. and he tells you how to define those boundaries, and you can put that in your Excel spreadsheet. And the point is that your mirror is good as long as the points fall anywhere within these boundaries. So that's one way you can reduce the data that you get from your table to let you know whether or not you have a good mirror. And if I remember right, this is the boundary where all the light is in an acceptable, what they call the airy disk, which I'm going to talk about in some other presentation. So this is probably like about an eighth of a wave mirror if all of the points are within this bounds. Now, this is an 8-inch f8 mirror. This has a line and some look like reasonable, generous boundaries around it. But now, what I want to show you is suppose you run that same mathematics on an f5 mirror. Now you can see things get a little bit more complicated. And this is part of the reason I suggest people making their first mirrors generally make f8 mirrors or f7 mirrors, because they're a lot easier to parabolize. When you start talking an f5 mirror, once you start getting outside the 40% zone, in order to have a good mirror, you don't have very much tolerance at all. That mirror's got to be dead on in order to meet our acceptable criteria. You start to have a little bit of tolerance when you get down here toward the center of the mirror. On the other hand, if you have an f12 mirror, the curve for the parabola is so shallow and the tolerances are so wide that you can actually come up with points that all fit on a straight line going across. A straight line, by the way, is a perfect sphere. It's the null condition, isn't it? It's no knife edge position. So any place where you've got a horizontal line, that means you've got a null condition. So if you've got points that are all inside this boundary but going straight across, that means that you don't need to parabolize the mirror. That a sphere is going to be within the acceptable boundaries, and you can use the sphere. And that is truly true of a 6-inch f12 mirror. And this just illustrates that with those formulas. Let me talk a little bit now about the raunchy screen when used at the center of curvature of a test for a parabolic mirror. Now, we showed that when all the lights from the optical system come to a focus, that the lines will be parallel, straight, and evenly spaced. Any departure from that, if it's an irregularity in the curve, they're just going to be wildly erratic looking lines. But if it's a spherical aberration that's being introduced, or in other words, a predictable form, what you're going to get is curvature of the lines. And you notice with this here, I think this is like an f7 mirror, an f8. Center line is fairly straight. The lines to either side are outward curling. And essentially, what you see is that the center, the lines are more tighter packed. You would get more of them in any given linear distance. So the center of the mirror here is farther from the focus of that zone, and then as you get toward the outside, the lines tend to spread out so that the focus is getting closer to where the screen is. Now, this is the screen behind all focus of a parabolic mirror, and you get this characteristic look of lines hooking out at the edges. And if you had the raunchy screen inside a focus, then what you get is this kind of a characteristic look with the lines bowing in. Kind of looks like a pumpkin or a basketball. There have been attempts over the years to try to characterize a parabolic mirror by just using this as kind of a quantitative test, saying, well, I think my lines are curved about enough. That test sort of works, but you have to be careful of it. One thing, or a couple of factors that enter into the arc of those lines is the actual diameter and focal ratio of the mirror, and the other thing is the spatial frequency of the lines and spaces. By spatial frequency, I'm talking about number of lines per inch. So if you standardize what your look ought to be with a 150 line per inch screen, then you've got to be doing your test with a 150 line per inch screen, and you've got to have the screen in exactly the same position, producing exactly the same lines. But if you've got an f7 or an f8 mirror, and you've started with a sphere, and you've just done some parabolizing strokes, and it's just starting to show a little curve on here, chances are that would be good enough, and you can say, aha, I am done, I'm going to have an acceptable mirror. And a lot of people have done it that way and had very good mirrors. You can't guarantee from this technique any quantification of how good your mirror really is, though. And I just want to show you that if you start with you get an f4 parabolic mirror, that the lines now become wildly divergent from a straight line, and trying to characterize those against some known standard is going to be considerably more difficult than the gentle curve you get when you're talking about an f7 or an f8 mirror. So when you're talking fast mirrors like f5s and f4s, this is not a very good technique to try to achieve the parabola by some known standard, just some quantitative known standard. The wire test, instead of a raunchy screen with just one line, you just have one wire instead of a screen full of wires, and you run that wire real close, essentially acting as a knife edge, but with two sides. And the advantage of this is that you can more clearly define the zone. You can define it because instead of having light and dark and some amount of gray in between, because it's one wire and it's a knife coming from both sides at the focus, you actually end up with a fairly well-defined wire and a fairly cleanly defined zone. That test works fairly well for very fast mirrors, but one of the problems is it's hard to define the center zones with it that way. In this case here, the 60% zone is the first zone where I could define any kind of a discrete distance and measurement with that test. When you start getting to the outer zones, then it becomes very easy to define. The caustic test you may or may not hear something about. And I just want to explain a little bit about some of the errors that go into these kind of testings where you're measuring spherical aberration. What you're normally doing when you're doing the test that I just described with a knife edge just inside of focus and just outside of focus, you've got a parabolic mirror and you've got a tangent at the surface, another tangent at the surface. The light is reflecting back, so it's perpendicular to that surface, and you've got a crossover point here, which is what you're really looking at. But if you were really to mask the whole mirror except for just a little circle here, the actual curve of that circle is going to produce a focus which is not at the intersection point, but it crosses the intersection point and comes out here. Now I've shown it for the edge of the mirror. If I show it for this place in here, then I've got an intersection that's here, and if I go further in, I've got another intersection that's about here. And essentially what happens is that all of the focal points for a parabolic mirror or a mirror with spherical aberration, all the focal points fall on what's called a caustic horn. And a very, very accurate and quantitative test can be done if you could put your knife edge on an XY carriage, so you can measure distance not only to the mirror but some lateral distance away from the center line of the optical axis, and null out each individual circle as it comes out of the mirror. But that's a very complicated test. It requires very, very precise setup. We're talking fractions of a millimeter are going to make a big difference in the way the test is read. So unless you have some very highly refined setup equipment for the test, this is not a test that's going to be very satisfactory to know that you got a good mirror. Now, those tests that I just described are the tests where you're defining your parabola by measuring the spherical aberration. What is a lot more interesting to do is to come up with null tests. When you have a null test, you just have one test answer. You don't have a interim results that you have to subject to another analysis. A sphere at the center of curvature is a null test. You get, with a knife, single knife, get a uniform grain. With raunchy screen, you get straight parallel lines. That's a null condition. You either know the lines are straight and parallel or they're not, or with a knife edge, you've got a uniform grain or you don't. Now, there are several tests that have produced a null return in one way or another. One is called a Mobsby screen, and that's used at the center of curvature. You got an artificial star at a known distance. You got a Dahl and a Ross test, which we'll talk about, and we'll talk about the autocollimation test. And this is, in my opinion, the best test. It's the one we use here in the workshop. We also have the star test. Now, let's talk a little about the Mobsby screen. We talked about the raunchy screen, and we showed that if you have a parabolic mirror and you introduce the raunchy screen, that you're going to have curved lines. Someone said, well, gee, instead of having straight raunchy screen giving back curved lines, why don't we pre-generate the curves the opposite way so that they will then return straight lines and give us a null test return? Well, a guy by the name of Mobsby came up with that idea, and you can buy a Mobsby screen. This is an enlargement of one that I have for a 8-inch f7 mirror. When you get a Mobsby screen, you have to define very carefully what the diameter and the focal length of your mirror is. And then you get the screen, which are pre-generated curved lines, and it must be put at a very precise place in the returning beam to give you the straight returning lines, or the null return. So although it's okay in principle, it's a little bit difficult to use. One screen is very specific to a specific mirror, and also this test does not apply itself very well when you start talking fast focal ratios. If you remember, when I was showing you before, long focal ratio mirror is just a gentle arc to the curves, so you can straighten those out. But an f4 mirror those curves got very wild, if you recall, and coming up with pre-generated curves would be very difficult. In fact, probably impossible to do. You also can do a null test on a mirror by considering a light source a long distance away. Again, if you recall, I said if you take a circle and you put a light at center of curvature, it's going to reflect back. And if you have an ellipse, you can put the light at one foci and your raunchy screen and knife edge at the other foci, and you can continue to stretch the ellipse. And the farther you stretch the ellipse, the closer you get to a parabola until that ellipse is so stretched that the foci are infinite distance apart, and then you have the parabola. So how far apart do the foci have to be before that ellipse is so close to a parabola that we can say that if we run a null test against that ellipse, we're within an acceptable tolerance for a parabola. And there is some mathematics that have calculated that. I have here a reference of Telescopes for Skyscrapers by Henry Paul, and there's some mathematics you can run. But let's just say you're looking at the glint of a reflection a couple of miles away. That's certainly far enough. You can run a null test. And people do that. If you go to Stellafane, you'll notice that there are Christmas tree ornaments hanging on the trees out in the woods. Those Christmas tree ornaments reflect the sun. There's a little glint on the corner of that Christmas tree ornament, which is essentially an artificial star some finite distance away. But it's so far that you can aim your telescope at that, and you can focus it, and you can defocus it, and you can run some star tests, and you can look for the null condition. Another way to get a null test with either a knife edge or with a raunchy screen is to take some auxiliary optic of some kind, introduce it into the outgoing light beam so that you're introducing spherical aberration into that beam so that by the time it returns to your eye and gets measured, you get a null return. And that's a fairly common test. This type of test, or something similar to it, by the way, is what was used in doing the Hubble Space Telescope. One issue you have to control when you're doing this test is the spacing between the light source and the mirror has got to be very precisely controlled. If it's not, you're going to introduce some error into that test. But it is a good test, and it's more often used for much larger diameter mirrors. If someone's doing a 24-inch mirror, a 20-inch mirror, they're apt to make a Ross lens. I certainly would. Probably the best test for a parabolic telescope mirror is what's called the autocollimation test. You don't often read about this in the literature because there is an auxiliary optic that's required for this test. And this is the mirror being tested, and it requires a flat mirror that's at least the diameter of the mirror that you're testing, and it has to be optically flat. And hopefully you can get it optically flat within a 10th or a 20th of a wave. So a lot of the text refer to the autocollimation test, but they dismiss it very quickly because they say, well, you have to have a flat, and since you don't, we won't talk about it. But this is actually about the best test you can do, and that's one of the reasons we use it here in this workshop. What you do is with a parabolic mirror, you put the light at the focus, not the center of curvature. And this is the flat mirror, and there's a hole in the flat mirror. The light is going to radiate from the light source. It's going to hit the parabolic mirror, and then, since we're actually working the telescope backwards, it's going to reflect off the parabolic mirror and going to go out in a columnated beam or a parallel beam. It will go off infinitely into space as a parallel beam. Just as if a star were sending light in and would focus it to a point, we're doing it in reverse. Okay, let's put a flat there and intercept that flat beam, send it back to the parabola. And if we do, then that light ought to refocus right back where it started. And of course you move the light, move the focus, and then you can look at it and examine it in the same method. There's two advantages to this test. One being that it's a null test, and the other is that it's a double pass test. The light comes from the light source, it hits the parabolic mirror to send a returning out columnated beam. That beam is re-reflected back, it hits the parabola again, forming the light beam that comes to a focus. By doing that, any errors that are on the mirror surface are going to be magnified by a factor of 2. So you get a more sensitive test than any of the other tests, even the other null tests. By getting a null test, you have no readings to take, no other analysis to subject your results to. If you get a straight raunchy lines, or you get a uniform grain from a knife edge test, then you have a parabolic mirror. There's nothing more to discuss. This is an example of a mirror done with an autocollimation test and with a raunchy screen at the radius of curvature. And what I'm trying to show is that this is exactly the same mirror. You can see that we have straight parallel lines. This is with 133 lines per inch. And these little divots here, this is a composite picture to put this together, and these are corners. Those little black things are not part of the image. But you've got, straight parallel lines. This is an f4 parabola, and even good, absolutely right out to the edge. This is the mirror, the primary mirror for my 12.5-inch Cassegrain, and this is that same mirror subjected to the raunchy screen at the center of curvature. And you can see how wild these curves become when done at a center of curvature. This is obviously not a null test. This is. You can look at that test result. Are the lines straight, evenly spaced, and parallel? If they are, you're done. If not, go rub the mirror until it gets better. The last test that you do is the star test. The star test is actually a very important test that we can all do. It's it can be a comprehensive test, but there are some fairly simple elements to it. You take your telescope and you aim it at a bright star. And you examine that star under a magnification that gives you about 20 times the aperture diameter. So if you have a 10-inch mirror, you're looking at 200 magnification. You take your focuser, you focus on the star, you focus an equal distance inside of focus and an equal distance outside of focus. The defocused image should be, you should see a slight central obstruction. If you've got a Newtonian reflector, of course there won't be a central obstruction with a refractor, but there'll be a central obstruction with generally most reflectors, because there's usually a central optic of some kind. And then a series of diffraction rings. When you look inside of focus and outside of focus, that central obstruction should be the same size, and the rings should appear identical inside and outside of focus if you have a system that's completely properly corrected for spherical aberration. If, when you do that test and you defocus the star inside of focus, and it's kind of blurry and there's not good defined rings and the light is concentrated toward the center, and then you go outside of focus and you have a fairly large central obstruction and well-defined rings, then your mirror is overcorrected. In other words, you've gone beyond the parabola to some form of hyperbola. If, on the other hand, when you're doing that star test and you run the focuser inside of focus and you see well-defined lines and a central obstruction, and you go outside of focus and the light is kind of a fuzzy ball toward the center and you don't have well-defined rings, then that's the reverse condition, and your mirror is undercorrected. And you've started with a sphere, you've gone to some series of ellipses, but you haven't gone far enough to be a parabola. So that's a fairly good test, and it worked quite well. That's the test they use at Stellafane, by the way, if you enter the optical competition. There are other things that you can tell about the defocused star, about your mirror with a defocused star image. I'm not going to cover that all here. It's very, very comprehensive. There's a book that covers that. It's called Star Testing Astronomical Telescopes by Harold Richard Suter. And anybody that's so interested and inclined, I'd recommend that they get that book and read it. And that's the end of what I have to say today. Thank you very much. I hope you've learned something. We'll talk more.